My complete research work is based on the design and development of conformal antennas, which should be lightweight also and can be applicable for the phased array systems. So today I'm going to present a lightweight conformal filtering antenna based on stacking of multi-corrugated polyimide films. So I'm from myself, Mohammad Ameen. I'm from Department of Electrical and Computer Engineering, National University of Singapore. So my presentation is divided into different sections. So first of all, giving a brief introduction about conformal antennas and the major design challenges of what we are facing while designing the antenna. Then moving towards the design of conformal filtering antenna, parametric studies and photographs of the fabricated prototype, performance comparison and summary and future work. So before going towards the work, what is conformal antenna? Conformal antenna is nothing but it's designed to follow the shape of a surface, primarily defined by the structural or aerodynamic requirements. So in literature, we can see that there are different varieties of conformal antennas are present. But at the main problems with that designs are it's difficult to integrate with curved surfaces. That means they are semi-conformal, rigid conformal. Once the antenna is fabricated in a specific conformal shape, we cannot conform into different shapes. So from the literature recently investigated, most of the investigated conformal shapes are cylindrical, spherical, conical, and some complex surface like some pyramidal shape. And applications include aerospace, automotive, smart satellite, wearable, intelligence, reconfigurable intelligence surfaces, etc. So the what are the most important challenges what I observed the designing of conformal antennas are. So in literature we can see there are thousands of conformal antennas, but most of the antennas are not conformal. I can say that they are not fully flexible. It's a partial flexible antenna. Once it is fabricated, we cannot change the shape. And the another important factor is that we are using this kind of polymer materials. We are using designing of conformal antennas, so we can get easily conform. But the main issue with this type of material is that the impedance bandwidth. So if we are designing an antenna with this type of material, the impedance bandwidth maximum we are going to get 0.1%. So our ultimate aim is to increase the bandwidth, and the most of the designs are design complexities. They are using metallic vias and more time consuming for fabrication. And for the satellite application, most of them are using some readily available PDMS and some other kind of materials. So Rogers materials, even most of them are soft materials, and it cannot withstand at high temperature. So these are the challenges what I'm facing the designing of conformal antennas. So I'm going to rectify some of the issues. So moving towards my proposed design, this is a work we in our group we have published in last year IEEE International Workshop on Antenna Technologies held in Sendai, Japan. So moving before going towards my design, so we can see this is a conventional patch antenna, microstrip patch antenna, which is having a ground plane and middle layer, which is a substrate layer. It could be either FR4 or any material. And the top radiator microstrip patch, it can be a square, rectangular, circular, any kind of shape. So this is like rigid, we cannot conform. So modification of this conventional antenna design, we have made a conformal antenna design by using we have replaced the substrate with the foam material, like this is called the PFO foam. So we just replace with the substrate with PFO foam and we can make conformal. But at the same time, this antenna is even conformal. We can see that we can conform to a cylinder with radius 20 mm. We can fully conform the antenna. But at the same time, the antenna is facing the problem of narrow bandwidth, as well as we can see that the gain response for different radius. So the shaded portion, we can see that the antenna working range, but out of portion also the antenna gain is positive. So in my work, what I'm going to design is that I'm going to design a lightweight antenna which is having more bandwidth, as well as the same time the filtering property is also included with the antenna. So moving towards the proposed design. So this is my proposed design. So this design is having five layers actually. So this is the ground plane of the antenna, and this is called the copper cladded polyimide material. So that means the one side is copper, the other side is polymer, because copper I'm using copper thickness is 12 micrometer. So 12 micrometer copper is very soft. So some metal is needed to combine with the copper. So that's why I'm using copper cladded polyimide. So the layer 3 and layer 5, that are the radiators actually. So this is called the primary radiator and other called the parasitic or secondary radiator. So, and the green color we can see that the green colors is this. I have replaced the previous design, the PFO foam, with this plastic screws. Actually, it's nylon only basically. And layer 3 and layer 5 is this copper cladded polyimide. So we have just combined what is that? We have made such a way that in this kind of geometry, so the antenna can provide broad bandwidth as well at the same time. The antenna is lightweight also, and it is conformal for all the cylinder radius. So before going towards the fabrication, we have done various parametric studies. So from these parametric studies, we can see that the antenna resonance, the antenna is giving three resonances actually, from 1.2, 1.25 and 1.35, because why we are concentrating in this region, our area of interest is at basically at L band at 1.2 to 1.3 gigahertz. So we can see that this from the antenna, the spacing is the most important parameter. So if a small change in the spacing, the antenna response is also changing. So from the parametric studies, we have concluded the antenna dimensions. So for the next stage, actually, we fabricated the antenna. So we fabricated the antenna is that we have just taken this material. So for the ground plane is the layer one. So we have just added some slots in the ground plane, and in the top main radiator and the secondary radiator, we have just taken this material by using laser cutting. We can see layer 3 and layer 5. We have cutted using the laser cutting, and we fabricated the antenna. And then we have just combined. We have tested with cylinders of different radius, cylinder radius 160 mm, cylinder radius 80 mm, cylinder radius 40 mm, and we can see that the antenna is same antenna which can be conformed to almost all the cylindrical surfaces. And one of the most important thing is the antenna lightweight. So the antenna is only coming only approximately 16 gram for the single antenna. So our ultimate aim is to go for future for the phased array application. So suppose if the antenna is coming like 8 by 8 array, this is only single antenna. So if we are going for an 8 by 8 array configuration, that means 64 elements. So approximately only maximum 1 to 1.5 kg, we can fabricate a 64 element array antenna. So that is one of the advantage. If you compare with the conventional existing materials like FR4 or Rogers material, the antenna size will be more than 15 kg will go. So moving towards the measurement results, so we have measured the input reflection coefficient and the realized gain for the flat case. So here we can see that for the simulation and measurement are not fully agreed. Its agreement is there because there are three resonances coming, but still due to fabrication issues, so one band is just touching minus 10 dB, but still the results are fine. So when we are comparing with the simulate measurement results for the realized gain, also we can see that uh, the the out of band range, the gain is coming negative. So that means the antenna can provide filtering response. Then further, we have tested the antenna performance with different cylindrical radius like uh, it flat case and cylinder radius 200 mm, 160 mm, 100 mm, 80 mm, and 40 mm. We can see that the resonance frequency is almost similar from 1.2 to 1.27 to 1.28 gigahertz. At the same time, bandwidth is slightly varying. When I'm increasing the bending, the bandwidth is slightly increasing, but still it is okay. Our area of concentrated region is 1.2 to 1.3 gigahertz. Further, we can see that the antenna gain obviously when we are bending the antenna from different cylindrical radius like this. So this is a flat case, the radiation is mostly concentrated in this region. So when we are going bending and more bending, the antenna beam width is actually reducing, beam width is increasing. So because of that reason, when at the extreme bending case, cylinder radius 40 mm, the gain is changing from 8.5 dB to 6.5 dB. Further, the front to back ratio is very good for this antenna of approximately 20 to 27 dB is coming. So further, we have plotted the radiation pattern for the complete frequency range from 1.17 to 1.36 gigahertz for different frequencies. So here also we can see that for all the frequencies, the antenna is providing directional radiation pattern, and also the difference between co and cross polarization is uh, difference is more than 15 dB. So still the antenna is working well for the application. So here I have measured the simulated and measured gain results for different frequencies and different bending. See, we can see that all the frequencies, while in the flat case the gain is higher, while moving extreme bending up to 40 mm cylinder radius, the antenna gain is reducing. So further, we have compared with the performance comparison, compared the performance of the proposed antenna with the existing antenna. So I can see from the literature, so we have compared almost all the works recently published in IEEE journals. So we can see the only three works I can observe for the L band, and also we can see majority of the works are based on the rigid conformal or fully fixed conformal, and filtering property is not included in almost all the antennas, and most of the antennas are thick, and also the design complexity is also quite high. So most of the issues what currently solve the conformal antenna is currently issue facing, we can solve by using this technique. So moving towards the conclusion, actually, a broadband filtering antenna is demonstrated using the basic idea is using corrugated polyimide films. The lightweight antenna design is a total weight of just 16 grams. Filtering functionality is also included with this antenna. Bandwidth enhancement by using stacking of primary and secondary radiators. And antenna is fabricated for the L band and tested for different cylinder radius from 200 mm to 40 mm cylinder radius, and bandwidth is also approximately 16% with a maximum gain of 8.6 dB at 1.29 gigahertz. So in future, our plan is to scale the antenna into larger configurations such as 2x2, 4x4, or 8x8 antenna arrays, which can be integrated into structures like aircraft skins or vehicle bodies. So this work was supported by Singapore Hybrid Integration Generation Microelectronics Shine. So thank you so much for watching the presentation.